Good day guys, welcome back to Wikiscience YouTube channel. In this video, I'll put you guys through on how to determine the heat energy of the system and as well as being able to determine specific heat capacity and how to calculate the heat capacity. So let's get started guys. Now, when it comes to heat energy is the total energy of molecular motion, and it is as well determined from the law of thermodynamics that your heat energy is proportional to the product of mass and your change in temperature. For every sign of proportionality, there is always need for a constant, and the constant introduced here is known as C with your change in theta. Here now we have it that M is the mass and C is the specific heat capacity of the substance to which heat has been applied. Specific heat capacity. We have your change in theta to be the change in temperature. Change in temperature. So this is how you determine the heat energy of a system. However, in some cases, you might not be given the specific heat capacity and you'll be given what referred to as heat capacity. So what do you do and how do you calculate the heat energy supplied to a system? In this case, you have to know that your heat capacity equals the product of mass and the specific heat capacity. So in replace for this mass and specific heat capacity, I can put ordinarily heat capacity, and it's going to be given that your heat energy of the system is equal to the heat capacity and the change in temperature. And that calls for the question that when you are told that the specific heat capacity of a system is said to be 1, what does it mean? Make your C the subject of formula. When you make your C the subject of formula, you have to be H over M and you have your change in theta. This simply means that the heat that is required here is 1 joule of heat, and the mass that which will be supplied with heat is 1 kilogram, and the temperature change will ordinarily be 1 degree Celsius or Kelvin. So it means that when you say 1 divided by 1, it will still give us 1. So it means that specific heat capacity of a substance is 1. And this means that 1 joule of heat is required to raise the temperature of 1 kilogram mass of substance by 1 degree Celsius or Kelvin. When it comes to the heat capacity being said to be 1, this simply means also that your heat capacity is taken to be the quantity of heat over the change in temperature. So in this case, it means that 1 joule of heat is required to raise the entire mass of a substance by 1 degree Celsius or 1 Kelvin. This has been a common question to some WAEC questions and some UTME questions. Please be able to answer this quite well when you come across them. Now let's take an example on how to calculate the heat energy of a system using any of these two representations that which we have been given. The question states that calculate the temperature change when 500 joule of heat is supplied to 100 grams of water, given that the specific heat capacity of water is 4200. Now in this question now, we have already that the heat energy supplied is 500 joules. Here we have the specific capacity to be 4200 and we have the mass to be 100 grams. Don't forget that this mass must be converted to kilogram. So in this case we have that H is equal to MC and we have change in temperature. Our heat is 500 is equal to the mass, which is 100. You convert it to kilogram by dividing by 1000. You multiply by specific heat capacity, which is 4200, and we multiply by the temperature change, which is unknown. From here we can able to determine that 0 will cancel 0 here, 0 will cancel 0 here, and 0 will cancel 0 here, 0 will as well cancel 0 here. So from here we can be able to denote that our temperature change is equal to 50 over 42, and that will give us 1.2 degree Celsius. So this is our answer to this question. According to first law of thermodynamics, which states that energy can be converted from one form to another. So therefore, there are various forms in which energy can be converted into heat energy. Let's consider, for instance, when you have your potential energy. Your potential energy to be given as mgh, where your m is the mass, g is the acceleration due to gravity, and h is the height. When this potential energy alone is responsible for the energy transfer, we say that our potential energy is maximum and our height here is maximum. We can as well have referred to as kinetic energy, in which our kinetic energy is given as half mv squared. In a case whereby the kinetic energy alone is responsible for the energy transfer, we say our kinetic energy is maximum as well as our velocity is maximum. Also, we can now have in the case of mechanical energy, in which it is a combination of your potential energy and your kinetic energy. None of these two energy is said to be maximum. Okay, there is another form of energy we refer to as electrical energy. Electrical energy can be expressed as I, V, and T. Where you have your I to be the current, you have your V to be the voltage, and your T is said to be the time. In this case now, according to Ohm's law, we can have it that V is equal to IR. Your electrical energy can be taken as I square RT in place of your voltage when the voltage is not given. However, in some cases, we can make this particular I here the subject of formula, which will be expressed as V over R. When this is done, we can as well express our electrical energy as V squared T over R. In this case now, these are the various forms in which you can have your electrical energy. But in case whereby electrical energy is expressed in terms of power, we can as well say that your electrical energy is given as the power times the time. Please take note of these various forms of energy that can be supplied into a body in form of heat. Now, when it is supplied to a body in form of heat, do not forget that your heat energy is expressed as mc change in theta, where your m is the mass of the body, c is the specific heat capacity, and your change in theta refers to the change in temperature. In cases whereby the specific heat capacity is not given, you can as well be given the heat capacity with the change in temperature. These are the various forms of heat energy. Now, according to the first law of thermodynamics, which is said earlier, these various forms of energy can be equated to the heat energy, meaning that in my calculation, I will express this various form of energy directly to this heat energy. And that only happens when heat is supplied directly to that body. That's when we say that energy supplied is equal to heat gained. However, there are forms in which, most especially when we are considering the electrical energy, that which the electrical energy will be supplied to two different bodies at a time. For instance, when water is in a container and electrical energy is supplied in form of heat to the water and the container. In this case now, you have to denote whether the container is a good conductor or a poor conductor. So when the container is a poor conductor, you don't need to consider the heat energy gained by the poor conductor. This is because the poor conductor will not share the same initial and final temperature with what you have inside it. In this case now, when you consider a poor conductor now, we can as well say that your energy supplied is as well equal to your heat energy. But in a case whereby you are dealing with a good conductor, for instance now, when you have an electrical energy supplied to a system where you have a calorimeter and you have water inside it. In this case now, the water here will gain heat. The water here will gain heat. And you have the container. So we say that container will gain heat. Here, it therefore means that your energy supplied is equal to the heat gained by the substance plus the heat gained by the container. So the addition of the heat gained by the substance and the heat gained by the container will be equal to your heat energy. We'll take a reference question on this aspect in which heat will be supplied directly to a body, and we as well supply heat to a body inside a container, and that container is an insulator. And as well, we now finally consider an aspect whereby electrical energy is directly supplied to a body inside a container, in which the container is a good conductor. So when the container is a good conductor, this is what we deal with for good conductor. This is for good conductor. For instance, when we take a question which states that a block of aluminum of mass m is heated electrically by a 25 watt heater. If the temperature rises by 10 degrees Celsius in 5 minutes, calculate the heat capacity of the aluminum. In this question now, you realize that the electrical energy was directly supplied to the aluminum block. It was not said to be in a container, meaning that this is a direct transfer of energy from the electrical energy to the heat energy gained by the what? Metal block. So we say, as we said earlier, that energy supplied is equal to heat gained. But here now, the energy supplied is in form of electrical energy. So here we consider the parameter of electrical energy that was given. We were given the power and we were as well given the time. So I will take PT equals, here we are asked to calculate the heat capacity, not specific heat capacity of the aluminum. So here we're taking it to be C subscript P, and we have change in temperature. Now power is said to be 25 watts and the time is said to be in 5 minutes, which is 5 times 60 when you convert to seconds. We are looking for the heat capacity, and here we have the change in temperature. The change in temperature is said to be 10 degrees Celsius, so I'll multiply by 10. From this particular expression, when we divide by 10, this will cancel this, 0 will cancel 0, and I have my CP to be 25 times 5 times 6. That will give us 750 joule per kilogram. This is what we refer to as the heat capacity of the aluminum. Let's take another example in which heat energy now is supplied to two bodies, in which the container is not a good conductor. Here is another question taken from UTME 2009 question 21, and the question states that an electric heater rated 220 volts 1000 watts is immersed into a bucket full of water. Calculate the mass of water if the temperature changes from 30 degrees Celsius to 100 degrees Celsius and the current flows for 300 seconds. Now in case like this, you realize that we are not given the heat capacity of the bucket, meaning that the container, which is the bucket, is a poor conductor of electricity. An example of such is a plastic bucket. So assuming we are given the heat capacity or even the specific heat capacity of the bucket, it means that it is a good conductor of heat. But here now, since you are not given, we will not consider the heat gained by the bucket. Simply we say that the energy supplied is equal to heat gained. And when we say it's equal to heat gained, what's the form of energy supply? We have the voltage, we have the power, we have the time. Since you can simply take power and time together as a form of energy so that it can be more easy and convenient to solve, we'll consider the heat gained. The heat gained now, since they are looking for the mass of the water, and we've always been given that the specific heat capacity of water to be 4200 joule per kilogram per Kelvin. In this case now, we can have it that we'll be taking MC change in theta because we've been given the specific heat capacity. The power is said to be 1000. The time is said to be 300 seconds. And we have it equals the mass which you're looking for, 4,200, times the temperature change, which is from 30 to 100 and can be taken as 100 minus 30. So here we have our mass to be given as 300,000 over 4,200 times 70. So here we have it to be 1.02 kg. So the mass of water that was boiled here is said to be 1.02 kg. This is when we're considering a poor conductor as the container. Now let's take another example in which we now consider a good conductor when the conductor now is given either the heat capacity or the specific heat capacity. Taking this last aspect derived from 2002 WAEC question essay 12B Roman figure 2, and the question states that a heating coil of resistance 20 ohm connected to a 220 volt source is used to boil a certain quantity of water in a container of heat capacity 100 joule per kilogram for 2 minutes. If the initial temperature of the water is 40 degrees Celsius, calculate the mass of water in the container. In this case now we have it that the electrical energy is supplied to water and even to the container because we're given the heat capacity of the container. So in this case now we say that heat supplied is equal to sum of heat gained. And from what we have denoted here, we realize that the energy supplied is the electrical energy in which we're given the resistance, we're given the voltage, and we are as well given the time. And that is V squared T over R as the electrical energy. And the sum of heat gained will be heat gained by the water, which is MC change in theta, plus the heat gained by the container. Because here now we have to add the heat gained by the container. Since we are given the heat capacity times the temperature change. This is for the heat gained by the container. Here now we have it that the voltage is said to be 220 volts times that is square times the time. The time is said to be 2 minutes, and that is 2 times 60 in seconds. Everything divided by the resistance. And the resistance we have here is said to be 20 is equal to the mass. The mass which you have here is said to be unknown times the specific heat capacity of water, which is 4,200, times the temperature change. The temperature change here is from 40 degrees Celsius to the boiling point, and the boiling point has been given in question to be 100 degrees Celsius. Therefore we have it to be 100 minus 40 plus the heat capacity of the container. Since this is for the container now, heat capacity of the container is said to be 100 times the temperature change. Now the reason we usually consider heat gained by the container is that when it is a good conductor, it shares the same initial and final temperature with the substance inside it. And the initial temperature of water is 40, while the final temperature is 100. So we take it to be 100 minus 40. So when we express all of this, 20 here 1 is 20 here 3. We can multiply this out and we will surely get 290,400, and that will give us, when we multiply all of this together now, it will give us 252,000 m plus multiply 100 times 60, and that will give us 6,000. Bring your 6,000 to this side, you have to be 290,400 minus your 6,000, which equals 252,000 m. So here we have it to be 284,400 equals 252,000 m. Divide by 252,000 divide by 252,000. This will cancel this, and we have now that our m is equal to 1.13 kilogram. So it means that the mass of water that boiled in this case is about 1.13 kilogram. Now we have come to the end of this video, but I want you guys to note that this video does not encompass the aspect of change of state of substance that has been heated. The water here was not set to boil away, and that's the reason we don't consider the heat associated with change of state. So in our next video, we'll be taking you on how heat energy is supplied to the system and which cause the change of state of this body. So questions will be displayed on the screen. I expect you guys to go over this question, answer them quite well, and if you have any question, you can release in the comment section. Thank you for watching.